Hello, in this video let's look at the single output differential amplifier. So sometimes we've seen differential amplifiers where the input was differential and the output was also differential. But many a times we want to design circuits where even though the input is differential, we want the output to be a single output. We don't want a differential output. So this circuit which does that is a very important circuit, very common circuit. It's known as an OTA. And it's a building block for a large number of components you'll see in analog design, especially op amps, filters, etc. So now let's look at the operation of the circuit in a bit of detail in this video. So the single-ended differential amplifier essentially looks like this. So the bottom half is what we've seen before. It consists of a differential pair M1 and M2, across whom you apply the differential signal of V1 and V2. You have a tail current source ISS. On top here, in difference to what we've seen before, you have an active current load, or this is known as current mirror. And you have a PMOS current mirror or a PMOS active load of M3 and M4 sitting out. And the output is pulled from this node, which is the V out. So first thing you see here is this is not a symmetric circuit because M3 is connected in a diode connected transistor, whereas M4 is a transistor in saturation. So obviously this is not a symmetric circuit, which means that in small signal this is not going to be virtual ground. M3 and M4, as I said, form an active load, and that forces, this is a current mirror, so it forces the current in M1 to equal the current in M2. Now when a differential signal is applied between 1 and 2, what happens is that a differential current force between M1 and M2, this active load is going to force the current in M1 through M4, leading to a large differential current which flows at the output node into the output resistor. Right? So if I think about how the circuit works, suppose I have a differential input of VID by 2 and minus VID by 2. I'm going to have a differential current of ID by 2 flowing through M1 and a current of ID by 2 flowing in M2. Now M3 is connected in a fashion such that the same ID by 2 is going to be flowing in M3. Now because M3 and M4 form a current mirror, this ID by 2 is going to be mirrored into M4. So M4 is going to carry the same current as M1. M2 is carrying a current which is ID by 2 in the opposite direction. So a net current of ID, which corresponds to the differential voltage, is going to flow at the output node and into the output resistance, causing a voltage to be developed at the output. Now when this ISS is implemented using an NMOS transistor, this becomes a 5 transistor circuit, and this 5 transistor circuit is known as the operational Transconductance amplifier, or the OTA. So let's look at the large signal modeling of the circuit. Let's assume that I've applied V in 1 and V in 2 to the differential pair, and my output is V out. Now when V in is much smaller than V in 2, M1 is in triode region. Right? When M1 is in triode region, what happens is no current flows in M3, which means no current flows in M4, and therefore what happens is this V out is a value close to 0 because M2 also remains in linear region. Right? Now as V in becomes closer to V in 2, right, M1 turns on, and so M1 starts to pull current. Now because M1 starts to pull current, M3 starts to pull current, which causes M4 to turn on, and which causes this V out to increase. So as V in increases, you see that V out also increases. And when V in is approximately equal to V in 2, that's when all these 4 transistors are in saturation, and I see a very large gain between the output voltage and the input voltage, or the differential input voltage. When V in becomes much larger than V in 2, then M1 is in saturation, pushes M3 and M4 to conduct a lot of current. However, so therefore this V out gets pulled up to VDD, pushing M2 into linear region, and hence very little current flows through M2. So Vout rises up to VDD. So you see that as Vin goes from 0 to much larger than Vin2, you see Vout initially starts out at 0 and eventually gets to VDD. Again, the gain is maximum in the circuit when all four transistors are in saturation, and that happens when Vin is approximately equal to Vin2. So that's where we're going to be doing a lot of our small signal analysis. Now, to ensure that M2 is in saturation, right, we need to ensure that this Vout is at least a threshold away from the common mode voltage. So which means that Vout has to be greater than V in Cm minus Vtn. And so if I want the swing at this output to be maximum, that means I want this term to be as low as possible, which means I want the input common mode voltage of the circuit to be as low as possible, right? So the lower the input common mode voltage, the higher the output swing I'm going to have. Now the input common mode voltage is going to be limited by what it takes to keep M1 and M2 in saturation. So it's going to be given by this VGS1 or 2 plus whatever is the minimum voltage required to keep this transistor, the M5 transistor, which is used to create the tail current, to keep that in saturation. That is going to be the minimum common mode voltage that will be needed for this circuit. Now, one thing we'll see about the circuit is it's very prone to asymmetries and variations, and hence normally we never use it in an open mode configuration, we always use it in feedback. Now let's look at the small signal analysis of the circuit. So we'll use the GMR out technique to extract the small signal gain. What do I mean by GMR out? Is we'll first extract the effective transconductance of the circuit, extract the effective R out of the circuit, and then define the small signal gain as GM times R out. Now to extract the effective transconductance, the technique used is to find the short circuit output current. So what we do is we short circuit the output and we want to measure what is the I out that is flowing in this shorted output. Let's assume that we have applied VID by 2 to gate of M1 and minus VID by 2 to the gate of M2. So to find this, solve the circuit, obviously we need to replace the transistors with their small signal models. And so this is the replacement of the circuit using small signal models. Couple of points I want to point out. First thing is you see that this common node here, that is the source of M1 and M2, is not grounded. Again, we know that this is an asymmetric circuit, so X is not the virtual ground. Second thing you see is because M3 is connected in a diode fashion, I have replaced M3 with a resistor whose resistance is given by 1 by GM3 parallel RO3. And second thing you know is that the gate voltage of M3 and the gate voltage of M4 are equal. In this case, we have taken it to be VGS of 4. Now, also what I want to point out is that this input voltage, this VID by 2 is applied between the gate and ground. Similarly, this minus VID2 is applied between gate and ground. And so therefore VGS1 is not equal to VID by 2 because this node is going to be at some finite voltage. So this is the gate voltage, not the gate to source voltage. So VGS1 is not equal to VID by 2. Similarly, VGS2 is not equal to minus VID by 2. And X is not a virtual ground. So now let's try and solve the circuit and try and estimate the value of I out. So first thing is, let's look at the voltage at node X. So the voltage at node X can be thought of as either VID by 2 minus VGS1 or minus VID by 2 minus VGS2. Right? In both cases, the node voltages is the same, which gives us a relationship between VGS1 and VGS2. Now to make the math simple or to make it less cumbersome, let me denote this 1 by GM3 parallel RO3 as some resistance RD. Now, let's look at the current flows in the circuit. Remember, this is an AC ground, this is an AC ground, which means that any current flowing through this resistor RD, that same current has to flow through the combination of these two paths, and that same current has to flow through the combination of these two before it hits signal ground. Which means the current flowing in this resistor is the same as the current flowing in this combination. Right? We can't say anything about this combination because you have an AC ground here and you have an AC ground here. But because you don't have any ground in this region, the entire current that's flowing here has to flow through this part and then flow up here. Which means the current from y to x is the same as the current from x to 0. So if I look at the current from 0 to x, if I look at the opposite direction current, it's going to be given by Gm2 VGS2 plus the current flowing in RO2, which is the voltage difference between the two ends of RO2, which is minus VID by 2 minus VGS2 divided by RO2. So that's the net current that's flowing from 0 to x. And if I look at current flowing from Y to AC ground, it is VGS4 divided by RD. So this current that's flowing from this 0 to x flows this way, flows up, and then flows from y to 0 again. So this current is equal to this current, which gives me a relationship that Gm2 VGS2 plus VID by 2 plus VGS2 by RO2 is VGS4 by RD. So here is one relationship between VGS2 and VGS4. Now if I look at the current in RO4, or sorry, in RO1, this should read RO1. If I look at the current in RO1, the current in RO1 is given by minus VGS4 divided by RD minus GM1 VGS1. Right? So if I apply KVL in this loop, what do I get is VGS4 minus VID by 2 minus VGS1. So this is nothing but the resistance, or rather the voltage drop across RO1 should be given by RO1 times the current flowing in RO1. Right? So now here I have a relationship between VGS1 and VGS4. So I have one relationship between VGS1 and VGS4, another relationship between VGS2 and VGS4, and I have a third relationship which I know VGS1 minus VGS2 is VID. So if I now take all these three relationships, I should be able to eliminate a few gate voltages. Finally, remember, we're doing all this analysis to calculate the value of I out. And this value of I out is nothing but GM4 VGS4, that is the current flowing from this node to this AC ground, plus VGS4 by RD, which is the current flowing through 0, this, and all the way here. Right, so this total I out can be thought of as GM4 VGS4 plus the entire current flowing through this path, which can be shorthanded to VGS4 by RD. Right? So again, you have an I out, which is again a function of VGS4. So if I express VGS4 in terms of VID, then I have solved the circuit. So I have three equations between VGS1, VGS2, VGS4 and VID, and I have a fourth I out, which is a function of VGS4. So if I can eliminate VGS1, VGS2 and VGS4 from the first three equations, I get my I out as minus GM1 into R1 times GM4 RD plus 1 by RD plus 2 R1 into VID. Or in other words, the effective transconductance of this circuit, which is nothing but I out by VID, is given by GM1 into R1 times GM4 RD plus 1 divided by RD plus 2 R1. So the effective transconductance is not just GM1, but it is also related to some of the other resistances in the circuit. Now let's look at R out. Now calculation of R out is again very intuitive. How do I calculate R out? I zero the inputs. So basically my inputs to M1, M2 go to 0. I apply a voltage at V out and I measure a current I out, right? And then the ratio of this V out by I out is the R out of the circuit. Now if you look at this I out consists of two paths. This node, again remember these two are AC grounds. So I have one path which connects this way all the way to this ground. I have another path which goes this way. So I can think of IO made up of two paths, an IO1 and an IO2. An IO1 which goes through M2, M1 and RD, and IO2 which goes only through M4. Now if I look at the resistance in path IO1, I'm going to travel through between the drain and source of this M2, between the source and drain of this M2 again, both the gates are grounded times RD. So the net resistance is R1 or RO2 plus R1 The way we've designed the circuit, R1, R2 are equal, so it's going to be 2 RO1 plus RD, right? So this IO1 is going to be VO by 2 RO1 plus RD. Now if I look at the gate voltage of M4, the gate voltage of M4 is given by whatever is the voltage developed across RD. Why do I need the gate voltage of M4? Because the value of IO2 is going to be the current that is being pulled from the drain of M4, which is going to be GM times VGS4 plus some V0 by RO4, right? So if I want to find VGS4 is IO1 times RD, and so therefore the current IO2 can be written as GM4 into VGS4, that is the transconductance current of M4, plus VO by RO4, which is the drain to source part of the current. And so let's now find the value of I0. So I0 is IO1 plus IO2. And so that's basically V0 by 2 RO1. So remember the voltage from this point, this is V0. So the voltage across IO2 path is V0. The voltage across IO1 path is also V0. So V0 divided by 2 RO1 plus RD plus GM4 into RD into V0 by 2 RO1 plus RD. Now this is the gate voltage of M4 plus VO by RO4. And so I can write my IO in terms of some 1 by resistance times V0, and so therefore my R out is the reciprocal of this term, which is RO4 into 2 RO1 plus RD by RO4 into 1 plus GM4 RD plus 2 RO1 plus RD. And so therefore now I can talk about the small signal differential gain, which is nothing but transconductance times R out. So I multiplied to reduce functions together. Obviously this is a little bit cumbersome to remember, but we know a couple of things about the circuit. One, we can obviously substitute RD as 1 by GM3 times RO3, which is RO3 by 1 plus GM3 RO3. We also know that GM1 is equal to GM2, and that is, I can denote it as the transconductance of the NMOSes. Similarly, GM3 and GM4 are equal, again because the current is equal, it's a current mirror, and I can call that GMP, or the transconductance of the PMOS. RO1s and RO2 are equal because again of same bias current, call them RON, and similarly I have ROP. So I have four terms, GMN, GMP, RON and ROP. And so therefore I can write my AD as minus GMN into RON, ROP by RON plus ROP into this term. So what you see is that the differential gain is given by minus GMN, or the transconductance of the NMOS, times RON parallel ROP. So this is similar to the gain one would have got in a differential amplifier with a PMOS load, multiplied by this correction factor which comes about because of the active current load mirror. Now in the case when this term is very large, and for simplicity's sake, I can talk simply as differential gain is just minus GMN into RON parallel ROP. So the differential gain is proportional to the transconductance of the NMOS times the total load at the output node. Now let's look at the common mode gain of the signal. Again, for common mode gain, I need to assume some tail currents resistance. And now I've applied an ICM to both M1 and M2, right? So I want to essentially find the gain from VICM to output node. Now, when VICM is applied to both, remember M3, M4 are going to force the two currents to be equal. When the same voltage is applied to M1, M2, currents in both the branches are equal, right? Now, when the currents in both the branches are equal, it means that the gate voltages are equal, which means that this node voltage is equal to this node voltage. It's a symmetric kind of circuit. So what I have in that case is my Vx and Vout are equal. And they're going to be equal as long as for all VICMs, right? Because as VICM changes, both M1, M2 current changes, M3, M4 current changes, leading to Vx is equal to Vout, right? And so we can treat this node, just for simplicity, we can treat it as a short circuit between Vx and Vout, just that there's no current flowing through this. And this makes it easy to analyze. So now if I draw the equivalent circuit in common mode, it basically consists of two NMOS transistors, which is the differential pair, connected in parallel. Therefore, they account for 2 GM1 and they account for an RO1 by 2 because there are two RO1s connected in parallel to each other. Similarly, the load, which is the current mirror load, can be thought of as two PMOS transistors, right, in which both the gates and drains are shorted. So I can talk about this as 1 by 2 GM3 parallel RO3 by 2. Again, because I have 1 by GM3 parallel to 1 by GM4, RO3 parallel to RO4, leading to this term. And then I have the tail current resistance RS. So now if I want to talk about the gain from VICM to Vout or Vx, the gain from VICM to Vout is nothing but a common source amplifier with source degradation. So again, if I assume this lambda to be 0, let's assume RO1 to be negligible and similarly RO3 to be negligible, what I get is my common mode gain is RD by 1 by GM plus RS, which in other words is 1 by 2 GMP to 1 by 2 GMN plus RSS, or the common mode gain is 1 by 2, 1 plus 2 GMN RSS into GMP by GMN. So if I talk now about the common mode rejection ratio, my AD is GMN times RON parallel ROP, and so my common mode rejection ratio is given by 1 plus 2 GMN RSS into GMP into RON parallel ROP. So again, what you see here is that RSS controls the CMRR. Higher the RSS, the higher the CMRR, the better you are. Now remember, this CMRR is coming about even if everything is matched. So this circuit has a common mode rejection ratio because it's a single-ended output, right? So even if all transistors are matched, you are going to have a common mode gain, right? And the other thing you see here is this RON parallel ROP. This is also related to the differential mode gain. So you see that higher the differential mode gain, you're also going to get a higher CMRR. So that helps. And so it's important to remember that the way to optimize the OTA, therefore, is to ensure that your RSS is as high as possible, which means that your tail current source needs to be designed properly.